In this video, we're going to complete the solution of the harmonic oscillator using the algebraic method. First thing we'll talk about is generating new solutions recursively from the Schrodinger equation. Then we'll talk about raising and lowering operators. We'll generate the ground state. And then finally, we'll get the quantum harmonic oscillator energies. So we start by wanting to solve the Schrodinger equation. Remember, from the last video, we have the Schrodinger equation, which is the Hamiltonian applied to psi, which is equal to E psi, for the time-independent Hamiltonian, is equal to h bar omega, and then the two ladder operators, a plus minus, a minus plus, plus or minus 1/2, applied to psi. Now, what we want to ask ourselves is, suppose we have a solution psi that satisfies the Schrodinger equation with energy E. What happens when we apply the A plus to psi? What kind of function do we get out of that? Well, the question is, if we apply the Hamiltonian to A plus psi, what are we going to get? Well, we know what A plus is, and we know the Hamiltonian is, right? So we have, and we know the commutating relation between A plus and A minus. So when we apply the Hamiltonian, which is this operator here, to the new function, which is A plus psi, which is also a function because an operator applied to a function gives you another function, we have h bar omega, A plus A minus, plus 1/2, and then this is all applied to A plus psi. Well, we can do that. We just factor everything through, and we get h bar omega, A plus, A minus, A plus, so we have a string of 3 operators in a row, plus 1/2 A plus, all applied to psi. Well, in general, we don't know what this is, but we do know that A plus and A minus have a commutating relation. And the first thing we can do, though, is we can factor out the leftmost operator, because since we apply the operators to the right, we have to apply this one first, then this one second, this one third. But there's only one here. So if I pull out the A plus, it becomes A plus out here. And then I get A minus, A plus, plus 1/2 applied to psi. Now, if you think about it, this is close, but it's not exactly what we had before, right? Before, we had A plus A minus applied, plus 1/2. Now we have A minus A plus, plus 1/2 applied to psi. But now the commutator relation between A plus A minus can save the day, because we have a commutator that says that A minus A plus commutator is equal to 1. But that means that A minus A plus A minus is equal to 1. So if I have A minus A plus and I want to convert it to A plus A minus, then I just have to solve for A minus A plus. A minus A plus is 1 plus A plus A minus. Right? So I put that in. I now have the A plus out in the front. I have h bar omega. I have A plus A minus plus 1 plus 1/2 applied to psi. And since we know that the Hamiltonian, which was up here, was A plus A minus plus 1/2 times h bar omega, I can pick out this term and this term are just the Hamiltonian and then have an extra 1. So this gives me A plus times the Hamiltonian, which includes this term, and this term. And then I have left over an h bar omega times 1. And so this is just A plus times the Hamiltonian plus h bar omega, all applied to psi. Okay, so now I realize that this function satisfies the Hamiltonian, and this is just a constant. So I can now apply the Hamiltonian to psi, and I get E. And so I'm left with A plus times E plus h bar omega psi. Now these are just constants, so I can pull them all out, and I get that the Hamiltonian applied to A plus psi is equal to E plus h bar omega times a plus psi back again. So what this is telling us is that the function a plus psi is also a solution to the Hamiltonian. But when we apply the Hamiltonian to it, we get an energy which is bigger than E by h bar omega. So a plus psi also satisfies the Schrodinger equation, but with energy E plus h bar omega. So this is a recursion relation. This tells you that when I apply a plus, I get another wave function back, another valid wave function, another solution of the Schrodinger equation. What about a minus? In just the same way, we can do the derivation for a minus. This is what we had for a plus. For a minus, we start by applying a minus to psi, and then putting the Hamiltonian operator on the outside. And we have h bar omega, and now I've chosen the other version of the Hamiltonian, that is a minus a plus minus 1/2 applied to a minus psi. Remember, these two are totally equivalent. I can then bring the a minus in, factor the a minus out from the front, and I'm left with a plus a minus minus 1/2 applied to psi. The commutator of a plus a minus is minus 1. So in the same way as I had before, I get a minus, because I pull that out in front, times the quantity h bar omega, a minus a plus minus 1 minus 1/2 applied to psi. But if I pick out this term and this term, I've got the Hamiltonian again, just like I had it up here. And so this gives me a minus times the Hamiltonian minus h bar omega applied to psi. But this is just E, and so this a minus then can be pulled through to give me my final relationship, which is the Hamiltonian applied to a minus psi is equal to E minus h bar omega a minus psi. So again, the function a minus psi is also a solution with its energy reduced by h bar omega. So this is why the ladder operators are called ladder operators. I prefer calling them raising and lowering operators because there's a reason. Eventually, we're going to talk, when you learn more quantum mechanics, we'll talk about things that are very similar, which are called creation and annihilation operators. Very similar. They raise and lower the energy. So these raising and lowering operators provide a recursive solution to the harmonic oscillator potential. And that's how we're going to do it. So let's start by looking at the nth state of the harmonic oscillator. So we know there must be a solution to it. What is the nth state? We're going to call psi sub n. So h bar, the Hamiltonian applied to psi sub n, is equal to the E sub n, the energy of the nth state, times the wave function back again. Right? This is just the solution to the Schrodinger equation for the nth state. Now let's apply the raising operator, a plus, to this state. Well, we know what that does, right? Because we apply a plus to psi sub n, and we get h. And then we apply h, the Hamiltonian, and we get a solution with a bit higher energy. Just like we saw before, we get En plus h bar omega times the function back again. This must be the n plus 1th state. So we are raising the state by 1, going from the nth state to the n plus 1th state. So if we call that the n plus 1th state, then we say that En, this is the energy of the n plus 1th state times a plus psi n, which must be psi of n plus 1, sub n plus 1. The same thing with the lowering operator. If I apply the lowering operator to the nth state, then it's going to reduce the energy by 1 by h bar omega, and that would be the E sub n minus 1 state times a sub n psi sub a minus psi sub n. So we can write that the raising operator gives you psi n plus 1, the next state up. And the lowering operator is applied to the wave function is the lowered state, the n minus 1 state. So when I apply the raising operator first and the lowering operator second, I get back to the nth state, or vice versa. So now, with these two operators, we have a prescription for generating all the wave functions which solve the harmonic oscillator once we know one wave function. So which wave function do we want to know? Well, the best wave function to know is the lowest energy state, because there's nothing below that. And so that gives us a method of calculating things. So these are my relationships. A plus psi applied to psi n gives me psi n plus 1. A minus applied to psi n gives me psi n minus 1. Now suppose we have the lowest state. We'll call it psi sub 0. It has an energy E sub 0, which is less than h bar omega. Because if it was bigger than h bar omega, then we could lower it to get a lower energy. So the lowest energy must have the lowest state must have an energy less than h bar omega. If we apply the lowering operator to this state, well, this satisfies the Schrodinger equation. It has Hamiltonian applied to psi 0 is equal to E sub 0 psi sub 0. Now, let's apply the lowering operator A minus. If we apply the lowering operator to this function, we can't get anything because there is no lower energy. We can't lower the energy below 0. And so we can't generate a valid wave function whose energy is less than 0. And so that means that when I apply A sub minus to psi 0, I must get 0. So this is now a prescription for calculating psi 0. This is a differential equation because if you remember, A minus has a differential form. It's sort of a boundary condition. So what's the differential equation this defines? Well, we just have to take A minus and plug it back in. So A minus, if you recall from way back, last video, is 1 over 2 h bar m omega, all square root, times the quantity h bar d by dx, that's the p, that's IP, and then plus m omega x, applied to psi 0 equals 0. Well, now this is an actual differential equation that I can solve. And there it is. This will give me the solution of the ground state. So let's rearrange this equation a little bit, and we get the following. So d psi 0 dx, that's this term here, is going to be equal to minus m omega over h bar times x times psi 0. Notice that since this is all equal to 0, all I care about is what's inside the parenthesis in psi 0. This can be factored away completely. So I'm just looking at rearranging this portion here. Well, this is solvable by direct integration. I just rearrange this, bring the dx over here, bring the psi 0 over here. I have d psi 0 over psi 0 equals minus m omega over h bar x dx. Fine, this is just the natural log of psi 0, and this is an exponential. Because this is not exponential yet, I'm sorry, this is minus m omega over h bar times x squared over 2 dx. Right? If I take that integral, I'm just integrating x dx. And so I get natural log of psi 0 equals minus m omega over 2 h bar x squared plus a constant. Well, as we did before, the ground state solution just gives us psi of 0 of x. If I take the anti-log here, I get this becomes a constant a when I take the exponential. A times e to the minus m omega over 2 h bar x squared. Well, this is just a Gaussian function. And we can normalize Gaussian function very easily. We take 1 is equal to the modulus of a squared, integral from minus infinity to infinity of e to the minus m omega over h bar x squared dx. And this is just the integral of a Gaussian. And we know what the integral of a Gaussian is. It's pi divided by, the square root of pi divided by what's in front of the x squared. And so we get a squared is equal to the square root of pi h bar over m omega. So my solution for the ground state is psi 0 of x is equal to m omega over pi h bar to the 1/4 power, because I have to take the square root of this to get a. It becomes 1/4 power, e to the minus m omega over 2h bar x squared. So we know the lowest order, the lowest function. Now we have to calculate the energy of that ground state. We can now apply the Hamiltonian in the form of the raising and lowering operators, because we want to do it the simple way, to get the energy. So H is going to be h bar omega times a plus a minus plus 1/2. Now we choose this one for a very specific reason, because when we apply a minus to psi 0, we get 0. Makes it really easy. So this means that when we apply psi 0, Hamiltonian to psi 0, we should get the energy of the ground state plus the wave function back again. Well, let's do that. We have h bar omega times a plus a minus plus 1/2 applied to psi 0. Well, that's easy enough. You have h bar omega times a plus a minus psi 0 plus 1/2 psi 0. Clearly this gives you 0, because that's the condition under which we got psi 0. So that goes away. And we're left with a ground state energy of h bar omega times 1/2. And we get psi 0 back again. So the energy of the ground state is 1/2 h bar omega. So it's half the size of the increment that you get when you raise and lower the energy. A couple points. The energy of the lowest state is always larger than the lowest energy of the potential well in which the particle resides. So the potential is 0 at the origin. That's the lowest value of the potential. The energy is never 0. That's called a 0-point energy, or a 0-point motion. So in a quantum system, you can never get to a 0 energy at the 0 of the potential. The energy is always higher than the lowest value of the potential. And so there's always some 0-point motion.